Korea, 1952. Badly wounded casualties are evacuated from a frontline MASH unit. Their savior is a revolutionary newcomer to the theater of war, the Angel of Mercy, the Bell 47 helicopter. The Bell 47 is immediately recognizable with its bubble canopy and distinctive dragonfly shape. But its primitive ancestor, a model built in 1931 by designer Arthur Young, was very different. It was a clumsy affair, driven by propellers on the end of the rotor blades. It would fly, but without stability. After 9 years of experimentation, a new model emerged from Arthur Young's barn in Paoli, Pennsylvania. Its rotor blades were hinged at the mast. To the surprise of many experts, Young had found that these hinged blades would follow the angle of the mast no matter where it tilted. There was a second coaxial rotor, which revolved slowly in the opposite direction to the main rotor and canceled out its tendency to twist the whole machine. Power was fed to the electric motor through a cable and controlled by a rheostat. Stability was still a problem. At a conference in Philadelphia in 1938, Igor Sikorsky raised a possible solution. Arthur Young was there.
I heard Sikorsky, and I was much impressed by his proposal to use a tail rotor with a single lift rotor, rather than the more complicated system which I'd been thinking of as an alternative to my first idea. The coaxial rotors, two going in opposite directions.
But before he got involved with the tail rotor, Young came out with his own special innovation, the stabilizer bar.
And I finally hit on this bar thing, which you can think of like a tightrope walker's bar. It maintains a horizon that keeps independent of the mast.
And it worked. Outdoor performance was a great improvement over the previous model, and for the first time, stable flight was possible in a wind. But there was still no directional control. Young could only vary the power of the 110-volt motor for climb and descent. Then came the flywheel, which could be tilted by remote control, causing the rotors to follow the angle of tilt. Directional control was suddenly possible. Young added Sikorsky's idea of the anti-torque tail rotor and came up with a new model. A beautiful, controllable helicopter, about 1/6 full scale. Not free yet, still electric-powered and controlled by cable, but ready to fly. And that same model, color a little faded after 50 years, still sits in Arthur Young's barn in Pennsylvania.
Now, first of all, we have a two-bladed rotor, 1, 2, and that's on a seesaw pivot. That makes it independent of the mast. But in addition to that, we have this other motion, which is this way, twisting the rotor, and that gives the control. Now notice that the twisting comes to this flywheel up here. Well, this flywheel normally maintains a horizontal position and hence keeps the rotor in a horizontal position even when the mast swings under it. That upper flywheel stays flat. The other thing is to transmit the inclination from these magnets, 4 magnets, which through these plungers tip what's called a swash plate, that's this black thing that I'm holding. And that in turn tips the flywheel, which tips the rotor. So that gives you the control. Of course, it has to be 90 degrees in anticipation. In other words, if you want to go forward that way, you pull it on this side and You can say due to gyroscopic effect, the flywheel tips then that way. And that in turn makes the blades go that way. In other words, the rotor will tip forward and pull the machine forward.
Test flights were entirely satisfactory. It was time now to go full scale. In September 1941, Arthur Young packed his model in a suitcase and went to see the Bell Aircraft Corporation. Larry Bell must have been impressed because Arthur got a deal and a place to work. The Bell helicopter was on the way.
Well, at first it seemed tempting to try all kinds of new things, and the chief design engineer whose office I was in had various ideas about how it should be done. And I found these ideas impractical and eventually just used the model itself, scaled up 6 times to make the full scale.
The Bell factory was located at Buffalo, New York, and in June 1942, Arthur set up his own specialized unit in a garage a few miles away at Gardenville. He wanted to build a full-scale helicopter.
But then when I read the fine print, it was to draw 2 helicopters, whereas my agreement was to make them. So I realized that that wasn't what I wanted. I didn't want to draw. I didn't know how to draw them anyway. The thing was to make it, and when you found out how to make it, then you could draw it.
Arthur recruited some of Bell's best machinists, and his new team, known as the Gardenville Project, moved into action. In less than 6 months, the first task was complete, and in December 1942, Bell Model 30, known as Ship 1, was rolled out. Ship 1 had no clutch, so the crew had to spin the rotors to allow the engine to start. The stabilizer bar, Young's unique development, was now a permanent part of the design. In the first tests to find out how the controls responded, Ship 1 was tied down with a fixed landing gear of widely angled struts for stability. Arthur Young was the first pilot, and he made these tethered hops with the help of his old friend and assistant, Bart Kelly.
At the very early stages, we hadn't refined the rotor so that we had it perfectly balanced. And as it would get up to speed, it'd start shaking. And this was a very critical question. Normally, one could expect that it would clear up, you could go through resonance. In other words, after it shook for a while, and as you got to a higher speed, it would stop shaking and be all right. So I was determined to get through resonance, come hell or high water, and I gave it the gun, and it did go through resonance and sweetened up perfectly. This was before we were flying, of course. And then I sort of shut it off and wiped my brow, and at that moment, Bart comes rushing out, holding a piece of paper, saying, "Don't go through resonance, you'll blow up."
Another incident almost ended in tragedy. A Bell Company executive, who was also a test pilot, insisted he fly Ship 1. Arthur Young tried to discourage him, and when that failed, tried to explain the controls. But the executive wasn't interested.
In any case, he got into the thing and jiggled the controls around until it started bucking, and the tail went into the rotor and gave such a jolt to the thing that he was thrown through the rotor. I thought this was curtains, the end of everything. I rushed over to him because he was thrown out about 30 feet, but he was all right. He was just broken wrist, but he didn't bother us anymore.
The crash set the program back. Ship 1 had to be stripped down and reassembled, and a new set of rotors machined. The young man shaping these rotor blades out of solid wood had been trained by Arthur in the pre-Bell days to make rotor blades for the small-scale models, at a time when the need to replace broken rotors was an everyday event. Ship 1 featured a vertically mounted Franklin engine. It was a focal point the day rival helicopter pioneer Igor Sikorsky made his only visit to Gardenville.
There was a great flotilla of Cadillacs with all the Bell executives bringing Sikorsky, and they came to this little garage and all got out and sort of lined up on one side, and the other side was the Gardenville crew, and myself and Sikorsky facing one another. And Sikorsky said, "I see you have the vertical engine." And I said, "Yes, I have the vertical engine." And that was the conclusion of our visit.
Arthur designed his own test equipment. He set up a system using scales to measure the torque or twisting force at the tail of the helicopter. Knowing this figure and the RPM of the Franklin engine, an exact calculation of engine power was possible. Franklin claimed 160 horsepower.
We could get very accurate figures on horsepower, and this was embarrassing to Franklin because we could never get the power that they claimed we could get from the engine. See, this way I could measure the power without any doubt about it.
The full-scale helicopter in tethered hover showed the same stability as the small model. In June 1943, Ship 1 was ready to be tested in forward flight. The only convenient place was a small grassy meadow outside the Gardenville building. Pilot Floyd Carlson found that under speeds of 20 miles an hour, it performed well. But when he attempted higher speeds, an old problem reappeared in a different form.
We had trouble with what we call 2 per rev. That's a vibration that sets in as you get going about 30 miles an hour. And in the conservative flying I'd done, I'd not run into it. But when Floyd started to go faster, he ran into this severe vibration. And we had to solve that, which we did by stiffening the rotor.
But it wasn't that simple. The problem needed experimentation. And rather than experiment with Ship 1, Arthur Young pressed one of his old models back into service. A solution was eventually suggested by Floyd Carlson. He proposed a system of bracing the rotor blades, which you can see at the top of the mast. In honor of his Swedish ancestry, it was named the Swedish Yoke, and it did the job perfectly. The first free flights in this form, in the large space of a Buffalo airfield, were an immediate success.
He took off and was immediately flying over 70 miles an hour with no trouble at all. We didn't have room for a passenger, but we gave the dog a ride. And actually, at one point, the wheel fell off. But there was no problem because I just stuck the wheel in like a caster while he hovered. Yes, that was a famous day.
After this success, Ship 1 emerged with a complete skin and a new paint job. It was now a fully fledged helicopter, the pride of the Gardenville project. The next test was to be a power-off landing under auto-rotation. This was the second with a mild flare or nose-up attitude. Then came the third.
So he flared even more, which meant that the ship landed at a 45-degree angle and then smashed down on the front. And it all ground up in itself, and then we were amazed to see Floyd just climb out. And someone said, "Are you all right?" And he said, "Yes, God damn it."
Arthur Young on the right looks at the damage, and the unscathed Floyd Carlson suggests a modification to the landing gear to prevent a repeat of the accident. Ship 1 will have to be rebuilt. September 1943. A new helicopter emerges from the Gardenville garage. This is Ship 2 with its enclosed cockpit. It was designed to have a family resemblance to the Bell Company's World War II fighter, the Airacobra. The only passengers to fly in Ship 1 had been Arthur Young's dog Brian and a bag of cement. Larry Bell, the company president, had still not flown. Now he was to get his chance. his first vertical ascent would be in Ship 2.
And that had a seat wide enough for 2 persons. And that was the one that Larry had his ride in. I think it was March 1944.
According to Bartram Kelly, Larry's reaction to his ride was that as an old farm boy, it allowed him to look at cows from an entirely new angle. There were many visitors to Gardenville, anxious to see and even touch this new marvel. Among them was a group of Russian generals.
And these generals were looking at it, and one of them in particular kept reaching in and turning knobs and things. And I said, no, mustn't do that. But he kept on doing it, so I slapped his wrist, and then they stopped. So I have the distinction of having slapped a Russian general's wrist.
Model 30 Ship 2 was a thoroughly practical, maneuverable helicopter, except that the 2-seater space was somewhat cramped. It would have appeared much earlier, but Bell's insistence on the cosmetic similarity to the Airacobra had slowed production down. But now, in the spring of 1944, with Ship 1 repaired and displaying a splendid yellow color scheme, it appeared that Arthur Young had fulfilled the terms of his agreement with Larry Bell to build 2 helicopters. And now it was time to put these machines before the public. These were still the very early days of helicopter flight, and there were records to be broken. This is the Armory in Buffalo on May 10, 1944. Floyd Carlson puts on a show for the officers and cadets of the Civil Air Patrol, and in the process makes the first indoor helicopter flight in the Western Hemisphere. His only problem is coping with the blinding glare of the spotlight. July 4th the same year, Ship 1 is the star of the show in front of a crowd of 42,000 at the Buffalo Civil Stadium. Again, Floyd Carlson is the pilot, and for most of these people, seeing for the first time a helicopter going through its bag of tricks, this is a rare glimpse of the future. But back at the Bell factory, Larry Bell's engineers, having learned some lessons from Arthur Young's project, were designing their own helicopter, Model 42. It was built like an airplane, with room for 4 passengers, but it would never go into production. Meanwhile, Arthur Young was building another helicopter, but it was not exactly authorized, and Bell management wasn't aware it was being built. This rare film shows how little attention was given to aesthetic appearance, but by now the Gardenville project knew what worked and what didn't. Ship 3 was a real helicopter, using all the best features of Ships 1 and 2. It became the basis of the Bell 47, America's first civil helicopter.
Well, we did get a windshield in the form of this bubble, which was dreamed up by a friend of mine who came. I'd known him socially before I went to Bell, Joe Parrish. He had the idea of taking a sheet of plexiglass, heating it in the furnace, laying it on a flat table, and then putting a template over it to confine the shape, and blowing with compressed air just the way you'd blow a soap bubble.
The Bell 47 would appear in many different versions, but the bubble became its signature. For Arthur Young, the arrival of the 47 meant the end of his association with helicopters.
The 47 was about to be a production model. We had the drawings all finished, and the production line was started, and they were beginning to come off the line. So I thought my task was done.
But the man who had begun working with model helicopters in 1931 had another reason for leaving this phase of his career. Arthur Young was fascinated by pure science and the study of philosophy. In August 1945, the world was changed forever by a single event. The nuclear age had arrived.
And this reminded me that I didn't want to go on wasting my time making machinery. It was fun to make machinery, but there were more important things. And as I put it to myself at the time, we needed a mental A-bomb, something that would enlarge our horizons as the physical bomb had enlarged mechanical horizons. That's what I spent the rest of my life on.
And while Arthur Young went off to pursue his philosophy for the post-nuclear age, the Bell 47, in its many different forms, military and civil, flew into history.
The AH-1S turret and rocket management is a system refinement based on Cobra weapons with which you're already partially familiar. The Chin turret system is a case in point. It has an M197 20mm gun with a capability rate of fire limited to 750 shots per minute on the AH-1S Series 50 ammunition. The turret is electrically driven in azimuth and in elevation. Direct drive DC motors through a gear train supply mechanical power for driving the turret. The servo amplifiers are in the Universal Turret Control Assembly, located on the right side of the aircraft at the gunner station. Positioning of the weapon is by means of the familiar helmet sight. It makes gun control virtually instinctive. By selection where the pilot or gunner looks, there the gun will point automatically. The gun moves left or right in azimuth 110 degrees, a total of 220 degrees. The normal slew rate is more than 80 degrees a second. In elevation, it varies from 11 degrees to 21 degrees up and 50 degrees down. With such rapid turret traverse, be sure when the gun turret is energized that the area is secured. This will prevent someone being accidentally struck by the gun should the turret be rotated. If there is a loss of any electrical power or master arm is turned off, the turret will go to emergency stow position 11 degrees up and 0 degrees azimuth. During ground maintenance operation of turret, the emergency stow circuit breaker should be pulled to prevent the emergency stow from activating. Here's the gun feed system. It is a proven design, classic in its simplicity. Note the similarities between the 7.62 gun feed system on the original AH-1G and the 20mm feed system on AH-1S. Conceptually, they are similar systems, but there are many refinements. Here's a small but important example. By activating the loading switch, this electric motor pulls the linked 20mm rounds from the box and pushes them into the section of flexible chute that connects to the gun feeder. This booster motor eliminates the excessive belt pull loads that would be found if the delinking feeder were the only source of power. The booster motor also eliminates the need to manually fill the chute during loading operations. Although this turret is a growth version of the proven M28 turret, the 20mm M197 weapon provides vastly improved combat punch when compared to the 7.62 round. This is test footage of the gun system taken during its qualification at Yuma. But this gun system has been through more than just an extensive Army test program. It is the same weapon which has been in operational use with the Marines on their AH-1Js. So it's a proven system, one which should enter the Army inventory with minimum growth pains. Recoil is obviously a problem with any 20mm cannon. You'll notice this single recoil adapter located above the gun drive assembly. There's also a compensation circuit running to the aircraft SCAS system. This means that appropriate aircraft attitude changes are made through the SCAS whenever the gun is fired. Which leads us to another electronic compensation. It's the way the gun takes its own Kentucky windage, the automatic corrections for aircraft speed and gun attitude. These small sighting corrections are automatically fed to the gun as a target is being tracked throughout the 220-degree field of fire. Turret system test and checkout is a simple routine operation. This single test set will check out the entire system. W1 connects to the aircraft power source. W6 is a multiple lead cable that connects to the gun control assembly through the fairing access door and to the logic control unit and test connector 19J1. Now you're ready for an operational check of the turret system. Use of the test set is detailed in TM-9-1090-206-12, but we'll just briefly look at some of the functions. There are several important safety considerations before starting a system checkout. All wing stores should be downloaded. W3J1 should be disconnected from W2P1. The gun, feeder, and feed system should be clear of ammunition. In short, no ordnance should be on the aircraft. These are all common sense procedures, but they must be done in sequence, so just follow your TM checklist, and you'll soon be ready to begin the operational check of all turret systems. You'll find operation of the test set straightforward. There are 16 keys for test selection and command functions, plus reticle, pass, and fail indicators. There are 9 separate functional checks, the first being power distribution and test set connection, followed by a test for fixed forward servo stability. There is a check to verify the gunner's turret stow position. There are 3 TSU tests: tracking, turret depression limits, and a tracking out of coincidence check. Slow turret slew and forcing function are covered in the next test. And the last 2 tests verify gun trigger application and release. When a fail condition exists, there are fault code numbers displayed on the test set. These numbers and the fault code table in the TM will help to diagnose the malfunction in the system. This has been a quick overview of the M197 Universal Turret. You may well ask why call it universal when all we've shown is the 20mm M197 gun. Well, it does accept other weapons. The M134, for example, the proven Cobra minigun, 7.62mm. And perhaps most important of all, growth capability is designed into the turret. So if future tactical needs dictate even larger caliber than 20mm, the system is designed to accept the M230E1 30mm chain gun. Now let's take a look at the rocket management system. Wing stores have been important since the first attack helicopter, and although the stores might not look too different than other Cobra versions, there is a significant difference in capability. This control and display unit is the heart of rocket management. It permits the pilot to select the precise rockets needed for specific mission requirements. We'll use animation to show the relationship between the zones of the display unit and the specific rocket tubes which they control. Zone 1 is the outer ring of rocket tubes on the outboard launchers, a total of 24. Zone 2 contains the top and bottom pair on the inner rings of tubes, again, the outboard launchers. This is a total of 8. Zone 3 is similar to Zone 1, the outer ring of tubes, only this time on the inboard launchers, again a total of 24 tubes. Zone 4 is similar to Zone 2, only inboard launchers again, a total of 8 tubes. Zone 5 is the 3 center tubes of all 4 launchers, a total of 12. Now you'll notice that the 5 zones have thumb wheel counters which can be set to indicate the type of rockets which are loaded in the specific zones by aircraft armament personnel. And just above each zone arm switch is a rounds remaining counter. The LED readout will decrease each time any rockets are fired, so the pilot knows exactly how many rockets and what type he has available. The zone arm switches are located below these rounds remaining readouts. These switches are pictorial and have a symbolic representation of the specific zone of rockets which they control. The first thumb wheel at the bottom of the panel selects rocket penetration in meters, thus enabling the explosion to occur a predetermined distance after foliage canopy penetration. The increments are in 5-meter intervals from 10 to 45 meters. There's also a super quick setting for point detonation. An additional bunker setting will detonate the rocket after penetration of dirt and logs up to 3 meters in thickness. Rate selects 3 rates of fire: automatic, slow, and fast. In general, the automatic setting will be used since that is the optimum firing rate for the specific type of rockets being used. Mode is a selection of firing. Quad, 1 rocket from each of the 4 launchers. Pairs, 2 rounds, 1 from each side of the aircraft. and single, one round, alternating from each side of the aircraft. Quantity is a multiple of the mode switch. It varies from 1, 2, 4, 8, and all. So if the pilot selects 8 for the quantity and has the mode of quad, the system will sequentially fire 32 of the selected rockets. The range switch activates the computer which sets the M439 fuses. The range is adjustable from 500 to 6,000 meters in 100-meter increments. The range switch has an A automatic position for future use with a fire control computer. Until the FCC is incorporated, the A position sets the M439 fuses for 3,000 meters. The press to test switch can be used either in flight or on the ground. The master arm switch on the armament panel must be in the standby mode in order for the test sequence to be initiated. The test validates the entire subsystem, including all associated aircraft wiring. We have spent quite a bit of time going over the cockpit display unit because understanding what it does and how it manages the rocket system is very important to armament personnel. Obviously, the loader must load specific rockets in their respective zones in order for the system to work correctly. Within each zone, the loading can be random, but different rocket types for each zone must be kept separated. Bear in mind that there may well be times when only partial rocket loads can be used. Warhead, weight, altitude, high ambient air temperature, and full fuel loads are factors which can combine to limit the payload that the S can carry for certain stringent missions. Using the bit features of the subsystem, a maintenance technician is able to detect, locate, and correct problems which may occur within the armament loads. Here, a round was not seated properly within the launcher. Or this tube has a rocket which has not had the hook connected. Even defective rocket motor squib can be detected with this bit equipment. Replacement of individual LRUs is easy. Each LRU has a mechanical fault indicator. The flag is tripped anytime a malfunction occurs, so replacement can quickly be made. One of the more sophisticated aspects of the rocket management system is the RC fuse subsystem. This is a completely automatic computer system which sets the fusing of each rocket on an individual basis. It automatically compensates for the up to 20% fuse tolerances and gives each rocket an individual fuse setting to achieve the specific range which has been selected. It's the most sophisticated part of the fire control system, but it requires no maintenance other than replacement of any defective LRU. Repairs of these faulty LRUs present no real problem at the intermediate level of maintenance. A single test set is sufficient to isolate the fault, make a diagnosis, and enable you to make repairs. The whole rocket management system has been designed for high reliability and maintainability. No introduction would be complete without a mention of some of the airframe changes that are found in the AH-1S. Perhaps the most important is this new 10 kVA alternator. It makes available through a rectifier 200 additional amps of DC power. That means that this new alternator or the start generator can operate the turret. Such redundancy provides a high degree of combat survivability and increases the probability of mission success if one system is damaged. This has just been an armament preview of the newest version of the Cobra, the AH-1S. Coupled with an already existing tow missile capability, it means that your aircraft can now bring an even greater variety of more potent firepower against a wider variety of targets. All Army aviation technicians perform valuable work, but when it comes to the 68M and J MOS, the work is perhaps even more important, because nobody contributes more to the direct success of the aircraft in its specific combat mission than the work of you armament technicians. Another man's finger may be on the trigger, but in a very real sense, the weapons are in your hands.
Amphibious assault. That's the environment for the Cobra gunships of the Marine Corps, the AH-1J and the AH-1T. The Cobras have a variety of missions throughout the amphibious operation. escorting the transport helicopters during the ship-to-shore movement, supporting their landings with suppressive fires, escorting and scouting for marine armor ashore, helping to control supporting arms, marking targets, and attacking enemy armor with a multitude of weapons. The AH-1J and T are virtually identical, except that the T is a tow cobra, able to fire the tow missile. There are also minor differences in maneuvering ability. Cobras operate in two planed sections wherever possible, for greater firepower and mutual protection. Maneuverability, agility, and small size make them difficult targets for enemy fire. This is an all-weather helicopter with IFR flight capability. It can operate at high altitudes if necessary, up to 10,000 feet. It's fast for a helicopter. Maximum speed in a dive with full ordnance load is 170 knots. The Cobra's prime operating area, however, is close to the deck where it's onto an enemy and past before he knows it's there. Cruise speed is 140 knots with a mission radius of 100 nautical miles. Visibility is unobstructed from the front seat, where the co-pilot usually rides. Both pilot and co-pilot are protected by armor plates and wear bulletproof vests. All Cobras carry 3-barrel 20mm Gatling guns, 750-round magazines. Rate of fire is 650 to 750 rounds per minute. This unusual weapon can be locked for the pilot to fire dead ahead, like a fighter plane. Or it can be trained, depressed, and elevated, fired from a remotely controlled turret by the co-pilot, using a telescopic sight unit. The gun can be trained to 110 degrees either side of center. The wide angles of fire, plus excellent true visibility, giving the Cobra fast response to threats from any direction. It can be depressed 50 degrees and elevated 15 degrees. Along with the 20mm Gatling gun, there is a choice of other ordnance. The Cobra can carry up to 52 high-explosive and white phosphorus rockets in 4 pods, with 1 7-shot pod and 1 for 19 rockets on each side. The tow Cobra can substitute 4 tow missiles for one of the rocket pods on each side, carrying 8 tows in all. Other combinations are possible, depending on the demands of the mission. Here is some of the available ordnance. Gun pods, with additional Gatling guns firing forward only. Fuel air explosives, and flare canisters, each with 8 flares, fired in pairs. The Cobra carries a lot of firepower, but if it's loaded with everything it can hold, fuel quantity has to be reduced. Normal procedure is to carry enough fuel for the mission, plus an ordnance configuration tailored to the job at hand. The Cobra's versatility makes it an integral part of the amphibious assault, another weapon in the Marine arsenal. It becomes the eyes of the armored column. It escorts and defends troop-carrying helicopters. It serves as a spotter for naval gunfire and artillery. It can mark targets for attack aircraft and control all types of close air support. Like all these systems, the Cobra exists to work with the ground troops. It is a tool of the landing force commander, assigned to the support of his units at any level, equipped for constant communication with command posts below, so that it can respond to changing needs as the situation develops. The Cobra's first mission in the amphibious assault is usually escort of helicopters carrying assault troops. At least 2 Cobras are normally used, deployed according to the expected threat and the terrain. In this case, the enemy threat is frontal, so the gunships lead the flight. The Cobras may fly behind if the threat is from the rear, as it often is on returning from the landing zone to the ships. If the enemy is believed to be a threat from all sides, the escorts may change their deployment constantly throughout the flight, but always in planned pattern. Station keeping and attention to schedules are vital during the ship-to-shore movement. Naval gunfire and supporting aircraft may be walking the flight in, laying down fires just ahead. Terrain is used wherever possible to mask the movement of the flight. The Cobras shift position as required by the terrain and by expected opposition. The escorts must be ready to drive off enemy helicopters, but must not leave the flight to pursue an enemy. The Cobras return any fire which could be a danger to the flight, but only long enough to distract the enemy from the transports. While the Cobras engage the enemy, the transports have a chance to get by without damage. At the landing zone, the lead Cobra pulls away from the flight and makes passes over the LZ to see if it's hot. The Cobra may fire 20mm shells or drop fuel air explosives to detonate booby traps and flush out defenders. As the transports approach, the gunships move to their second major task, support of the helicopter landing, with landing zone suppression fire. The troops and the transports are most vulnerable during offloading. Cobras go into a protective pattern above the LZ, usually a butterfly, firing at any targets which could threaten the landing. The attack helicopters may break their pattern to respond to calls from the ground commander for strikes against specific targets around the LZ. The Cobra's job here is protection of the landing. They fly their protective patterns as long as the transports are on the ground, then normally escort them back to the beach unless the ground troops are in trouble and need their support. The return flight always takes a different route. The area below is hot. Supporting fires may walk the flight back to friendly territory. Again, the Cobras shift deployment as needed to guard against the most likely threat. The escort mission usually ends at the beach. Now, let's look at other Cobra missions as the amphibious assault proceeds. The Cobras pick up a Marine armored column. Escort and scouting for service convoys is another of their jobs. The attack helicopters have standard escort patterns for ground units, just as they do for transport helicopters. If the surface unit comes under enemy attack, Cobras respond with suppressive fire to allow the ground unit to get by, or to cover it as it turns back. The ground commander may ask the gunship to scout ahead of the convoy, conducting reconnaissance by observation or by fire. The Cobras often shoot into suspected defensive positions to draw fire and reveal the enemy. If an enemy position is discovered blocking a route of advance, the ground commander may ask the Cobras to search for an alternate, less well-defended attack route. The task here is to help the ground commander conduct his attack effectively. The Cobras become the eyes and ears of the armored column, expanding its field of view. The Cobra pilot can drop in on a ground commander to discuss a complex situation. This is called a Zippo brief. The ground commander has a set form for the brief. He is able to give the pilots only the information they need for the mission in organized fashion. In this case, the Cobra is to mark a target for jet attack. High-performance jets are unable to slow down to consult maps and pick out targets. A Cobra can sneak out of concealment nearby and mark the target with white phosphorus. Or he can stand off 4,000 meters and lob his Willie Pete rocket onto the target. And stay there to control the mission, advising the jet pilot by radio that the marker is on target for a specified distance off. The Cobra can coordinate supporting fires, popping up from concealment to observe a situation. Most Cobra pilots have completed schools for both artillery and naval gunfire coordination, and can also serve as forward air controllers. In addition to radio contact, Cobra pilots can land at artillery positions for first-hand planning or for passing on of missions. Even though this Cobra is coordinating supporting arms, it carries a variety of ordnance to be ready for any mission assigned. When a Cobra pops up from concealment, it may be for more than observation or control of supporting arms. It may be for direct attack on enemy armor. The tow Cobra can be a deadly killer. Two Cobras lie in wait. Their primary targets are anti-aircraft vehicles and tanks, then armored personnel carriers. One Cobra pops up. The other remains hidden. The lead Cobra pinpoints the target location after a quick look, and the co-pilot passes the information to his teammates. The second aircraft then pops up at a different location, and it fires. After firing, both Cobras take evasive action and move on to the next attack position. An attack on enemy armor may also involve two other Cobras further from the target to divert the enemy's attention and furnish protection for the attacking Cobra. An attack is often coordinated with diversionary raids by other supporting arms as well. Cobras begin to engage with tow when enemy armor gets within 3,000 meters or so of the FIBA, while the enemy is still occupied with other attacking elements. Stop him. Turn him around, or at the very least drive his troops out of the armored carriers and into the open, where they are slow and vulnerable. That's the object of a tow attack on enemy armor. Those are the tasks of the Cobra in an amphibious operation. Success depends on the aircraft's ability to operate from many types of amphibious ships, and on those ships maintaining a supply of parts and ordnance to support the Cobra mission. Many tasks depend on the Cobra's ability to operate after dark and in reduced visibility, with all aircraft IFR equipped and their pilots fully qualified. Cobra squadrons are ready for immediate deployment at any time, with aircraft, spare parts, ordnance, and all gear ready and marked for embarkation. Cobra squadrons spend about a third of their time aboard ships or at bases away from home. The squadron is in constant training to upgrade proficiency and combat readiness for both people and equipment. It's a long road to combat qualification for a Cobra pilot. It has to be. Prepare him for the variety of tasks given to a Cobra squadron. The normal road runs directly from college to officer candidate school for 10 weeks. Then to basic school for 6 months or so of air and ground tactics. And on to flight school for a year to 18 months, first in fixed-wing aircraft and then in helicopters. When he gets his wings, he has about 200 hours of flight time, and he's been in school and training for at least 2 years, without counting college time. When the new pilot reports to his squadron, he's usually looking at still another year of training to be combat qualified. On escort duty, scouting for an armored column, working with high-performance jets, attacking enemy armor on its own, the Cobra has carved its own niche in the arsenal for amphibious assault. Today, it is an almost indispensable weapon to the Marine Corps.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
The only reason for an airplane to exist is to go fast. At the Great Air Meet in Rheims, Glenn Curtis set a world's record of just over 43 miles an hour, and the quest for speed was on. In 1913, Maurice Prévost was flying a streamlined Dépôt-Dessin monoplane at 126 miles an hour, and Europe claimed the lead in aviation speed. Immediately after World War I, quest for speed became a catalyst for the development of fighter planes. Countries which had not invested in new engines for their wartime fighters would, for reasons of national pride, invest in new engines to race them eastward. Then, in America in the 1930s, the situation reversed itself. Civilian aircraft, like the Travel Air Mystery Ship and the GB, Waddell Williams racers, became even faster than military aircraft. The reason was simple. Same engines were available to both civil racers and military fighters. The fighters had to carry guns, bombs, oxygen, and radios, while the racers were built only for speed. The world's absolute speed record was passed from country to country. And as the racers became faster and more powerful, they also became more expensive. America's Howard Hughes could afford to build his own racer, and with it set a land-plane speed record. But the absolute speed record of 440 miles an hour was set by a Macchi MC-72 seaplane in 1934, financed by the Italian government. Then military aircraft came back into the lead as the Heinkel and Messerschmitt firms competed for the title. Messerschmitt Bf-109R set a speed record of 469 miles an hour in 1939, a record that lasted for many years. When the jet aircraft came out, speed records rapidly accelerated, the British breaking 1,000 miles an hour in 1956 in a Fairey Delta II. Speeds continued to climb, finally reaching 2,193 miles an hour in 1976 by the Lockheed SR-71, alias Blackbird. While speed was the object, there were many other benefits in creating ever faster aircraft. Improvement in fuels, streamlining, lubricants, materials, and the list goes on. Speed produced not only prestige and pleasure, but also utility. The speed record setters ultimately paved the way for commercial transports, business jets, and private planes.